Okay, so for today, I'll talk about AWS contribution to the open source community, how AI is evolving, and so must the stack, and finally, building with vLLM on AWS. So at AWS, we've made some contributions across the infrastructure stack. Most notably, in 2021, we partnered with PyTorch and Meta on several initiatives, such as TorchServe, Torch Elastic, the S3 plugin. And today, very excited to be partnering again with vLLM, that is now part of the PyTorch Foundation, by providing cloud credits for the CI, a number of contributions across several teams, not just on GPU, but also Trainium support, a number of vLLM ecosystem integration, and finally, we made vLLM part of the deep learning container so that it is easy for anyone to get started. So in order to support this open source innovation engine, AWS provides a modular, a flexible stack composed of building blocks across compute, storage, and network with open interfaces. This allows you to build frameworks for the constantly evolving LLM use case for different accelerators and optionality in mind. So it might be worthwhile to pause and take a look at some of the current paradigm shift and some of those trends and see some of those implications at the infrastructure level. So, you may all be familiar with the transformer architecture already, but primarily there are three different phases: the tokenization, which is CPU bound; the prefill, which is GPU bound; and the decoding phase, which is known to be memory bound. Another trend is the shift from input heavy to output heavy token ratio. So, back in 2021, stuffing the context window using RAG for summarization and translation was pretty common. And as we shifted to chatbot, multi-turn conversation, you can see the ratio shifting. And finally, to today, reasoning model and agentic workflow are really pushing the token ratio to be more output heavy. So we'll see how reasoning models are changing the compute and memory pattern with a bigger emphasis on memory. And so in order to mitigate the memory bottleneck and work across those different challenges around memory, there's been several innovations across different frameworks and different workloads. vLLM with page attention for serving. For training, a number of innovation with multi-query attention or group query attention. A number of hardware are now supporting lower precision types and allow you to quantize even further. And we are seeing different frameworks allowing you to do different caching strategies or different cache offloading strategies as well. And finally, disaggregated architecture. So it's pretty common for vLLM and SGLang to support this new type of architecture. If you think about initially, when you had one inference engine running on one node or one host, you have the prefill and the decoding on the same machine. So when you perform decoding, very often your GPU will sit idle, and that would be a waste of compute. And so there was a need to decouple, also known as disaggregated architecture, so that you can have more flops or more specialized hardware for the prefill, and then maybe less flop and more memory optimized resources for the decoding clusters. And then, you need some kind of data transfer technology as well to transfer the KV cache. And NVIDIA Nixel is a new communication collective supporting those data transfers. And so now you have different nodes, different worker for those different stages, but as well, maybe you have multiple worker that had previously processed your KV cache, right? So one of the biggest optimization is to reuse the KV cache and having a cache hit. And so you need to be able to route or to have some kind of mechanism to do KV cache or model aware routing so that you can reuse the KV cache and optimize for latency and reduce your time to first token. Another trend is mixture of expert. If you, look at DeepSeek, Qwen, or Kimi, they're all based on MOEs type of architecture. MOEs only need to activate a fraction of the expert. So, during training, maybe you only need to update 2 out of the 8 expert, or maybe you need to activate only 25% of the weight, right? So inherently, you can expect a 2 to 4x better cost performance for training and inference. On the other hand, MOEs have a lot more parameters, and so it does require a lot more memory just to load the model and serve the model. You may be familiar with the 3D of parallelism, right? Data, tensor, and pipeline parallelism. These are all different strategies on how to scale across multiple nodes, your training or your inference workload. And they all share very similar characteristics in terms of communication pattern. They have very symmetric data transfer and very fixed volume across different nodes. So when you scale MOEs or mixture of expert, you shard different expert across different nodes. This is also known as expert parallelism, and you need to do an all-to-all communications. And so MOEs break those assumptions and those communication patterns previously known through the different strategies, right? So you can expect a 3 to 6x more communication than dense model. The volume between different experts is very hard to predict, and the nature of the communication is asymmetric in nature. So Amazon provide Elastic Fabric Adapter, which is a networking interface to allow you to, author and build and compose for those advanced, networking patterns. EFA bypass EOS and allow you to do RDMA, so direct accelerator to accelerator communication. EFA relies on libfabric, which is the library to allow you to author those advanced communication patterns, right? libfabric is open source and integrated with other standards and other communication collective, such as OpenMPI, NVIDIA, Nickel, NVSHMAM, and Nixel. It's just not on the networking layer that you can leverage EFA. You can also use EFA for GPU direct storage. So you can read from FSX for Lustre, for example, and feed your GPU directly, bypassing the CPU, for example. And finally, we covered networking and storage. On the compute layer, vLLM provides a great platform to run many model architecture across different accelerators, right? We covered before how the prefill and the decoding are becoming more specialized. And so vLLM give you more options by selecting not just NVIDIA GPUs, but Inferentia, Trainium, Graviton, or maybe AMD and other accelerators, so that you can really cater for a specific task, or maybe pick a better price performance accelerators. And to make that easy, vLLM is now part of the deep learning AMI and container. So we've encapsulated all the library dependencies and complexities, all the drivers and runtime. We optimize across the stack so that it's very easy for anyone to get started using vLLM on AWS. So whether you're looking to implement an AI gateway or routing, using different framework, maybe you're looking to deploy vLLM or SGLang using disaggregate architecture. Maybe you're looking to do some more advanced networking using EFA and other communication collectives, or maybe KV cache offloading, using different storage, or maybe using Ray for fine-grained GPU allocation, or maybe you want to author custom kernels. AWS provide a flexible and modular and different building blocks with open interfaces for you to run those frameworks, optimize those frameworks, or maybe build the frameworks of to more workload. A great example and case in point is the Amazon Rufus. That team deployed the shopping assistant that was used during Prime Day and was able to scale to over 80,000 Inferentia and Trainium chips. There's a great blog post. Feel free to check it out. And there's more details on that blog post. And then finally, we have an open source repository called AI on EKS with inference charts, blueprints, and guidance, so that it's very easy for you to get started with vLLM or Ray on AWS and EKS or Kubernetes. Okay, with that concludes my talk, and I can open up the mic for any questions.
Thank you, Fee. Well done. Does anyone have any questions for Fee while he's on stage? All right. I'll walk the mic around.
Hello, my name is Dishan. So I have a question that is it possible that you can divide your load on a multiple GPUs using the smaller GPUs? For example, if your required memory for the vLLM is like 48 GB and you have small clusters available, small GPU clusters available, you can divide your load among using some open source library?
Yeah, so vLLM allows you to do multi-node or tensor parallelism. So you can shard your model across multiple nodes in order to run your model that wouldn't fit on one node initially.
Okay, thank you.
One more question here.
Hi, former AWS employee here. So I'm really excited to see all the incorporation of vLLM and other open source into the AWS lab frameworks. But how does like fully managed solutions like Bedrock, which is used by a lot of companies these days, can take advantage of all these underlying infrastructural enhancements that you are bringing in the AWS infra layer?
Sorry, can you repeat the question?
How can fully managed solutions that are working at the model layer, like AWS Bedrock, use these enhancements? Are they already using this, or what's going on?
Yeah, I can't share all the details, but the Bedrock team is certainly contributing to the vLLM project, via the open source channels. And so, they are using vLLM, for serving those models.
Great. So if I'm used Bedrock, so all of these things, the vLLM serving is already integrated into Bedrock. That's your answer?
So so here what I'm sharing is like more the open source, more the self-managed stack, right? And so obviously you can combine by having a router that can route to some Bedrock models, but also self-managed models as well.
Thank you.
Any other questions for Fee before he wraps up his talk?
And I'll be here, if anyone has any follow-up questions. Thank you.
Awesome. Thank you, Fee.